Let's look at this problem right here. We've got a uniform 50 kilogram slender rod. It's at rest initially in the position shown. Then this force of 600 newtons is applied. Determine the angular velocity of the rod when the rod reaches vertical. All right, it's important to kind of visualize where it starts, where it ends, right? It is starting right here in this position, this green bar. It is ending right here in this position, right? This wheel would be down here. This wheel would be right about there. Visualize where it starts and ends. And it really hasn't really collided with the wall just yet. Remember that when we have collisions, we should do conservation of momentum, conservation of energy. It's, right before it hits that wall, what's the angular velocity of the rod? So don't tell me 0 because it has, hit the wall and stopped. It's right before it hits the wall. All right, let's use conservation of energy, right? Potential plus kinetic plus any non-conserved work equals potential plus kinetic. Potential could be gravity and spring. Kinetic could be linear and rotational. Non-conserved work could be FDM theta. I like to gravity, spring, linear, rotational. And I like to go ahead and write out the whole thing. I don't know if you do too or not, but gravity, or I could start with spring, mgh initial plus 1/2 kx squared initial plus 1/2 mv squared initial plus 1/2 I omega squared initial plus, if we have any FD and any m theta, equals all the final. mgh 1/2 kx squared final 1/2 mv squared final 1/2 I omega squared final. Now let's don't forget, this is the height of point G. Where's point G? Point G is right here, and really kind of visualize this. Point G final is right there. It's kind of a big point. So the MGH is always the H of the center of gravity, G. And really visualize. Don't go too fast there with the MGH. Visualize where that point G is initially, where that point G is final. Also, this is the velocity of point G. This is the I of point G. Okay. Now, you probably didn't even write this spring right here. There is no spring. There is no spring, so no need to write 1/2 kx squared, but sometimes I just do that anyway. Did it start from rest? A lot of times it starts from rest. If it starts from rest, then the V and the omega initially are 0. All right, are there any forces times distances? Yeah, well, that's 600 Newton force, right? That's an external force. I think it acts a distance. Is there any moment times theta? Here we're talking about an applied moment. No, I don't see any twisting moments on there. So let's say no m theta. And all right, so it simplifies down a little bit. All right, let's think about this MGH. Now, you can set your ground, your datum level, your 0 height wherever you want to. So sometimes it's helpful to set your 0 height where it begins or where it ends. But, sometimes it's just easy to visualize. This is the ground. Why don't I set my 0 height to be at the ground? So initially, my height would be what? 2, right? Initially, it's in the middle of this. That G is at 2. And then final, think about this. The bar would be straight up. The bar is 5 meters long. Final, the location of the center of gravity would be 2.5. See that? All right. Okay, let's just go ahead and start filling this in. The mass is 50 times 9.81 times 2 meters. All right, how about this force times distance? This 600 Newton force is acting a distance of this distance d. And it goes all the way right up to the wall. This is a 4, the hypotenuse is 5, a squared plus b squared equals c squared. That distance is 3 meters. And the 600 newtons is in the same direction as it's traveling, that 3 meters. So that's a plus 600 times 3. That's all we have on the left-hand side. On the right-hand side, we have mg. And remember, it says visualize that height of the center of gravity is 2.5 meters. Plus 1/2 mvg squared. I don't know that. I wasn't really given that. I don't know if that is right off the top of my head just yet. So let's write it as vg. And 1/2 ig. What is the I of a slender rod? The I about the center of a slender rod is 1/12 ml squared. So this would be, I've got the 1/2 right there out in front, but then inside here for the I, it's 1/12 m. So 50 L, the total length 5 squared times omega squared. So that's my equation right there. But I've got two unknowns, right? Velocity of the center of gravity g and the angular velocity. And it said I'm trying to find the angular velocity. Are those related? Are those related? Well, I know that v equals r omega. If I could just find this r is not always the radius. Sometimes, yes, it is. But this is the distance from the center of rotation. The distance from the center of rotation. Well, this is not really just rotating about some, point. This doesn't have a clear center of rotation. This is in translation and rotation. Let's think about the instantaneous center. Let's think about the instantaneous center at the end. I mean, this instantaneous center is changing throughout the problem. But over here on the right-hand side of my equation, this is at the very end. So let me find the v equals r omega. Let me find the instantaneous center at the very end. So let me find the distance from the instantaneous center of zero velocity at the end of the problem. At the end of our problem, what is happening? This point has to be going up. This point has to be going over. So remember, go back and review the instantaneous center method. Or if we know the direction of the velocities, then our kind of radial lines are, okay, my instantaneous center would actually be right here at point A. And that's fine. That's fine. And so this g, the distance that g is away from the instantaneous center, would be this 2.5. 2.5. V equals 2.5 omega. Right? Vg is equal to 2.5 omega. I would plug that in right there. I'd be real careful to square the 2.5, right? 2.5 squared and omega squared. And then I could solve for omega squared, solve for omega. All right. See if you get omega of 2.73 radians per second. Now, this equation just gave me 2.73. It didn't tell me positive, negative, and technically, to get my answer, I just took the square root. So this could be positive 2.73 or negative 2.73. So I've got to visualize and I've got to give it a direction myself. But I think you can see that this would, if the center of rotation is up here, this would be going clockwise.